I am gonna assume you guys can hear me okay. It's muted from your side, but hopefully you can hear me. And if not, then we'll just repeat it when we figure it out. Oh, can you hear me, Ivan? Well, I can't hear you, but I can hear the banging. So I'm gonna assume it's working. Okay. So, hello, good morning. Welcome to our last class of the term. Very exciting. You guys have been doing excellent work. So keep it up. We are almost done. So a couple quick reminders about what's left. So tomorrow you have your chapter 5 quiz and your last mini quiz. I recommend that you do the mini quiz prior to the chapter 5 quiz so that you can see what types of questions come up on the content that we cover today. The homework is due on Thursday of this week, so make sure that you get that in on time. You can submit any homework from the entire semester for half credit until Thursday night. On Friday, we'll be processing the homework grades, and at that point, your homework grades will be added to Moodle. So by Saturday morning, you'll know what your final average for the grade for this class will be, and that will help you make a decision about whether or not to take the optional final. So I will send an email out either Friday night or Saturday morning once the grades are all processed, and you can check that out. And I'll give you just a reminder of what the optional final would do for you so you can make an informed decision about whether or not you want to take it. So hopefully that works out well for you in either direction. So today we are finishing up chapter 5 with a section called Total Change and the Fundamental Theorem of Calculus. And so when we talk about this, this is sort of the bridge between Calculus 1 and Calculus 2. So if you go on to take Math 128, you will start with this and then sort of build from there. Okay, so I'm going to go ahead and switch over to the dot cam. Okay. And so what we're doing when we talk about the fundamental theorem of calculus is we are mostly formalizing things that we've already been doing. And that will make more sense once we sort of talk through it. So let's talk about what the fundamental theorem of calculus is, how it'll sort of impact what we've been doing, and all that sort of other good stuff. So the fundamental theorem of calculus says if f prime of x is a continuous function on the interval a to b, then the integral from a to b of f of x dx, so this is what we've been studying, the area under the curve, which we know represents the total change, is equal to the original function at b minus the original function at a. So let's think about this in context for a minute. Let's assume we were looking at the area under a velocity curve, and the area was 20 meters. That would tell us that the original function, which is position, changed by 20 meters. What the fundamental theorem is saying is if we had the position function, we could look at the starting position at A, the ending position at B, and their difference would be 20 meters, right? And for us, that feels like, well, yes, of course, right? Those are the same thing. But we've been working under the premise that we don't have the original function. Right? That was the whole point of this. If we had the original function, we could figure out how much it changed by subtraction. But we've been talking about, well, we don't have the original function. We have the derivative of the function. And how do we use that to talk about the original function? And so in Math 128, one of the things you'll do is you'll say, how do we take the derivative and find the original function, right? So the opposite of taking a derivative, you'll be doing anti-derivatives, right? Going in the other direction. But for us, what we're going to talk about is what sorts of information do we know about the original function from using area under the curve, and how do we write it in a way that we can then formalize our notation about the original function. And so a lot of the work that we're going to do is work that we've already done sort of conceptually, but we haven't written it down formally. So this is sort of the practice of writing things down in a formal mathematical manner to do the things that we've already been doing. So you'll find that a lot of stuff we do today is stuff that we've already done similar types of work, but now we're going to learn how to write it up in a meaningful way. So example 1, suppose ice is forming on a pond at the rate of dy dt equals the square root of t over 2 inches per hour. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, estimate the thickness of the ice after 5 hours. So I would like you to do this, and I want you to think really carefully about things like what variables are we using? How do we write our answer with the correct units, right? How do we set this up? So this is similar to problems we've been doing. There's nothing particularly different about this problem than other things we've been doing. So I want you to think about how you would approach it. And then when we go through it together, we'll look at how do we write this up really sort of formally using the fundamental theorem to get the same answer than what we get doing it sort of informally in the way we've been doing it before. Okay, so take 2 minutes, see if you can figure it out. Like I said, include units. So think about what the units are going to be, and then we will go through it together. Okay, take about 30 more seconds. All right. So hopefully your inclination was to integrate the rate, right? We have a rate, we want to integrate it, see what shakes out. That's what we need to do here, but we're going to formalize how this sort of pairs in with the fundamental theorem. So our integral here is going to be of the rate, which is the square root of t over 2, and we're going to use dt because our variable is t. Now let's think about what the bounds are going to be. We want to estimate the thickness of the ice after 5 hours. So that means going from time equals 0 to time equals 5. Okay, so we can get the total change in the thickness of ice by integrating from 0 to 5. Now, what does the fundamental theorem tell us? It tells us that the original function we can use to set these equal. And so here, the original function is going to be y, because the derivative is dy dt, the derivative of y with respect to t. So that means this is going to equal y of 5 minus y of 0, okay? Where y is the original function and dy dt is the derivative, which is this rate. So the fundamental theorem says if we had the original function, we could measure the thickness of the ice at time 5 minus time 0. That would also give us the change in ice thickness, okay? So what we are really looking for here is the thickness of the ice after 5 hours. So we want the measurement of the thickness of the ice at time 5. So if we were to rearrange this question to isolate this, we would need to add y of 0 to the other side. So we get y of 5 equals y of 0 plus the integral from 0 to 5 square root of t over 2 dt. So what does this say? It says the thickness of the ice at time 5 is equal to the initial thickness plus the change in thickness, okay? So the change in thickness is what we've been calculating, up until now in other sections of the course. So if we plug this into our calculator, we're going to get 3.726. And we need to think about what the units are. So here the rate is in inches per hour and time is in hours. So the hours units are going to cancel and we get 3.726 inches. Now, what's happening in the background, if we just integrate this as is, and we state that that is the solution, means that we are assuming that the initial amount of ice is 0 inches, okay? And that is a totally fair assumption in this scenario because we're talking about water and then we're talking about it just starts forming, which means that time equals 0, there was 0 ice because it just started forming. If it hadn't just started forming, it would have said something like, oh, you know, we start with X amount of inches of ice or something of that sort. So this is a fair assumption, but we need to pull it out and make it public that we are assuming that the initial amount of ice is 0 inches, so that the amount of ice at hour 5 is 3.726 inches. So part of the benefit of setting things up in this way is that when we have an initial amount that's not 0, we remember to include it to find our solution. Okay, so again, we're mostly doing what we were doing before by reasoning through, but now we're sort of thinking like, okay, how do we formalize this and make sure we didn't miss anything? Okay, so let's take a look at the next example. So a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when T equals 0. The coffee's temperature is changing at a rate of R of T equals -7, 0.9 to the T degrees Celsius per minute with time in minutes. Estimate the coffee's temperature when T equals 10. So there's a lot of numbers in this problem and we have to figure out where they go, how we set it up. But what I'd like you to do is to try to set up the integral that's going to represent the total change in coffee's temperature. Then use the fundamental theorem to set up a relationship with the original function, and then use that to answer the question about the coffee's temperature at time equals 10. Okay, so take 2 minutes, see how much you can set this up. Again, you really want to write it down so you have it formalized, and then we will go through it together in just about 2 minutes. Okay, take about 30 more seconds. Okay, so we need to figure out all the pieces of this and how we set this up in a formal way. So here we have the rate that we are going to be integrating. So there's only one function here. So when we start setting this up, we know that we're going to be integrating this particular function. So we can start there. Okay, so the first question is, what are going to be the bounds? Well, remember that this rate is in degrees per minute, which means that minutes is our independent variable. So minutes is what we need to put on the bounds. So we're looking at what happens from time equals 0 when we bring in the cup of coffee until time equals 10. So our bounds here are 0 to 10. That's in minutes. We want to know how much did the temperature change. And so what the fundamental theorem says is that's going to be the same as if we had the original function, which is temperature at time 10 and temperature at time 0, we could subtract them and it would tell us how much it changed. So we need a way to represent the original function. We don't have anything in this problem that tells us what variable to use, but there is a convention in math that if you have a lowercase letter as a rate, usually we use the uppercase version of that to talk about the original function. So I'm going to write this as r of 10 minus r of 0. But again, you don't have to. You can call it f of 10 minus f of 0, whatever makes the most sense to you. So what are we trying to find here? We want the coffee's temperature at time equals 10. So that's what we are trying to solve for. So in order to solve for that, we are going to add the initial temperature over. So we're going to get r of 10 equals r of 0 plus the integral from 0 to 10, -7, 0.9 to the t, dt. So the temperature at time 10 is the original temperature plus the change in temperature. Now, the change in temperature is a definite integral, which means that we can plug this into our calculator because we have a function that we're working with. Okay, so when we take that and we plug it in, we are going to get -43.27. And let's talk about the units. So here, this was degrees per minute, and then the independent units are minutes. So minutes cancel, and we get -43.27 degrees. So that's the change. The temperature decreased by that amount. So now we have to consider what was the initial temperature of the coffee. So there's two different temperatures presented to us. The cup of coffee's temperature is 90 degrees and the room is 20 degrees. And so since we are studying the change of the temperature of the coffee, we are going to choose the 90 degrees as our initial temperature, which means that the temperature after 10 minutes is the 90 degrees where it started, minus 43.27 degrees. We're going to crunch that number and we are going to get 46.73 degrees. Okay, so the 20 degree was extraneous information that we didn't need in this scenario. All right, and so the key things to remember here are that we do have an initial temperature that does need to be taken into account to answer the question about the temperature at time equals 10. Okay, so again, this is just another example of how we set this type up. Now, let's take a look at an example where we are now going to consider something graphically. So the figure below shows the rate of change of the quantity of water in a water tower in liters per day during the month of April. If the tower had 12,000 liters of water in it on April 1st, estimate the quantity of water in the tower on April 30th. So you can see this is in days, this is in liters per day, and we are trying to approximate the change. So there's two things I want you to do. First, I want you to set up an integral to represent what we are looking to find here using the fundamental theorem. We don't have, we don't have a variable to represent the function we're looking at, so let's just call this f of t. Okay, so we want to set up an integral to represent what we're looking for. And then I want you to solve that integral with the fundamental theorem for the piece that we want to find, and then use the graph to determine, right, the change in water over this 30 days. And as a reminder, this is the 0 axis, right, the t-axis. Anything above will be positive change, and anything below will be negative change. There's a couple different ways you can approximate, so it doesn't have to be perfect. but give it your best guess. But again, you're looking to find the final answer, but also to set up something in terms of the fundamental theorem. So take 2 minutes, try it out, and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's start by setting up our integral. And so we're looking at the area under the curve of f of t dt to help us understand the total change. We want to know what happens over the month of April. So day 0 to day 30, 30 days. And we know that's going to be the total amount of water on day 30 minus the total amount of water on day 0, right? So what we're looking for here is the total number of water on day 30 on April 30th. So if we solve for that, we can add the f of 0 over. We get f of 30 equals f of 0 plus the integral from 0 to 30 f of t dt. So what does this say? This says the amount of water in the tower on day 30 is equal to the initial amount of water plus the change in the amount of water over the 30 days. Okay, so the question is, what numbers do we know and what do we need to figure out? So f of 0 is the initial amount of water. That is a value we know because that's given to us in the setup. If you go back, it says the tower had 12,000 liters of water on April 1st. So here we have 12,000 plus, and now we need to determine the change in the amount of water over the 30 days. And so we have 2 pieces that we have to consider here. I want you to notice that this first chunk is underneath the curve. So that's going to mean we're losing water. And then from 12 to 30, we are above the x-axis, which means we are adding water. So we're going to treat these 2 separately and then compile them at the end. So for the first 12 days, what I said is this looks an awful lot like a triangle. So to approximate this area, I'm going to use 1/2 base times height. Okay. So again, you don't have to do it that way. You could have approximated based on, the volume of 1 cube, which we'll do later, but you should get something relatively close to what I get. So the base here is 12. And what about the height? So remember, when we're talking about integration in this context, this is negative. So we have negative 50. So 1/2 times 12 times negative 50. that's going to give us negative 300. So that means we've lost 300 liters of water over the first 12 days, approximately. You should get something between like negative 200, negative 400, no matter how you approximate. Now let's look at the area above the curve. So what I notice here is that there's not a good sort of triangle or rectangle shape because we get cut off right here. So I'm going to approach this one a little bit differently. So the way that I decided to do this was I said, okay, I'm going to approximate the area of one block, and then I'm going to approximate the number of blocks, right? That's another method we could use. So when I tried to find the area of one block, I noticed that they each have a base of 6 and a height of 50. So each block has an area of 300 liters, okay? So then I started counting the number of blocks in this area above the curve. So I have 1, 2, 3, 4 blocks that are completely there. Then I kind of looked at, okay, if I pair these two together, so this area here plus this area here, that makes a block. So I'm going to call that block 5. And then I did the same thing with this area over here. So let me do a different color so you can see what I'm talking about. Right? If I pair, you know, this area and this area, that gives me at least another block. So I'm approximating that there's about 6 blocks worth of area. Here you could say 6.5. I think either is reasonable. So if I have 6 blocks and each block is worth 300, that gives me an area of 1,800 for the area above the x-axis. So for the first 12 days, I lost 300 liters, but then I gained 1,800 liters, which means that my net change was plus 1,500, right? 1,800 minus 300 is plus 1,500. So when I come over here to my integral, I'm going to add 1,500 as the total change over that 30 days. So I had 12,000 and I added 1,500, which means that at the end of the month, I had a total of 13,500 liters of water. Okay, so that's how we approach this. And again, writing it up more formally helps us see the pieces that we need to find versus what we already know to help us compile to get the value that we want. Okay, so we're going to look at another graph problem. And so we're going to be given the graph of a derivative. It's on the next page here. And what we want to do is we want to use the graph of this derivative to help us understand the values of the original function. I'm going to trace this because this is a little bit lighter on the screen than on my paper. Okay. So let's walk through what we see here. This is f prime of x. Okay, this is 1. This is negative 1, not 7. Oh, that kind of looks like a 7. Negative 1. And we have the values from 0 to 6 for our function. In addition, we know that f of 0 equals 2. So not f prime of 0, f of 0. So this is the original function value. We want to use this information with the graph above to fill in the following table of values. It says make sure you mathematically justify this, which just means you should be using the fundamental theorem to do your calculations. So let's do the first one together, and then I'll have you try the others. So the first piece of information we want is what's happening at x equals 1, and we know what's happening at x equals 0. So we set up the integral from 0 to 1, so the one we have, the one we want. And if we integrate our function, we know that that's going to be f of 1 minus f of 0 by the fundamental theorem. What we want is f of 1. So if we rearrange this, we get f of 1 equals f of 0 plus the integral from 0 to 1 f prime of x dx. Okay, so we're trying to get this value. We know f of 0, that's the one that was given to us. So we get 2 plus, now the change from 0 to 1. All right, well, we can get that by doing a little triangle here, right? We do 1/2 base times height. The base is 1, the height is -1. We get -1/2. So we get 2 plus -1/2, and that gives me 1.5. Okay, so that's the value of f of 1. To get the value of f of 2, we're going to integrate from 1 to 2, and then continue to go down the table. So each time we go to the next point, we're figuring out how much more the function changed by using things like rectangles and triangles. All right, so I'm going to give you 2 minutes to see if you can fill out this table. Then we'll go through it together, and we'll talk a little bit about the implications of doing this particular type of problem to help us understand more about the original function. Okay, take about 30 more seconds. All right, so when we set up integrals for each of the values we're trying to find, what we find is that we want the one from before plus the amount we changed. So what we can do here is we can go through and figure out how much we changed between 1 and 2, and then add that to the value of 1, right? So we have the value of 1 plus the change. So from 1 to 2, we end up with this rectangle with a base of 1 and a height of -1. So that means that we are subtracting 1 from the value we had before. So 1.5 plus -1 is going to give us 0.5. To get the value at 3, we are again going to calculate how much we change in the next part. So from 2 to 3, we again have a base of 1 and a height of -1. So we have 0.5 plus -1, and that's going to give us -0.5. From 3 to 4, we have a triangle, so 1/2 base times height. So that's going to give us -0.5. So we have -0.5 plus -0.5, which is going to give us -1. And then there's a shift. So now from 4 to 5, what we notice is that now we are above the x-axis, which means that our area is going to be positive. Okay, so from 4 to 5, when we do 1/2 base times height, the base is 1, the height is +1. So that gives us plus +1/2. So -1 plus +1/2 from this change is going to give us -0.5, right? We become less negative. From 5 to 6, we have a rectangle. So it's a 1 by 1. So we have -0.5, the previous value, plus 1 is going to give us +0.5. So we're using what we know about definite integrals and area under the curve to figure out how much we changed so that we can get new values of f of x. This is really powerful because we are literally able to then plot these points to get a sense of what the original function would look like. And we do have some ideas about that from our graphing section, but this is giving us exact values on the original function that we could graph, right? And the only reason we are able to do this is because we have a value on the original function. If we did not have that piece of information, we would not be able to get these other values. So that's a really critical piece of this particular problem. Okay, so now we've done a couple graphing problems, and the next example is really going to tie in a lot of the work we've been doing for the entire semester. So we're going to be looking at a problem that asks us to use derivatives and antiderivatives and to sort out when we use which one and to answer all sorts of questions in a way related to physics. So here's the situation. Suppose the velocity of a moving object is given in the graph below. Okay, so this might be a car driving away from home or a ball rolling away from, a child or something like that. Some object is moving. Part A says, describe the motion of the object over the first 10 seconds. So think about what kind of information you would want to give to describe the motion of this object. So you'll probably be doing things like towards and away or forward and backward, something to indicate a direction. And notice that over the first 10 seconds, some of the area will be positive and some will be negative. So we'll want to calculate those separately and think about how to talk about them. Part B says, what is the acceleration of the object during the first 8 seconds? Well, this is a graph of velocity, and we know that acceleration is the derivative of velocity. So now we're using the graph to think about the derivative from 0 to 8. Part C, when are we accelerating, decelerating, constant? So again, that's asking you to think about the derivative at different places. And then part D, suppose that at time t equals 0, the object's at its home base. How far away from home base is the object at time equals 4 and time equals 12? So again, we're now looking at areas and we're considering what's going on at time 4 and what's happening at time 12 and how we might visualize that. So you may want to draw a picture like we did for the car that was driving to and from home the other day. I think that's a good way to help visualize what is happening. And so try that out, right? There's 4 parts to this. It takes a little bit to think back to all the things we know how to do, but try your best. I'm going to give you about 3.5 minutes to try these parts out, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. All right. So for part A, we are talking about describing the motion over the first 10 seconds. So that means we are going from 0 until 10, and we want to talk about what's happening in some sort of way. So what we notice is that at time equals 4, we have a change in direction, right? So we have positive area until 4, and then negative area between 4 and 10. So we want to split this up into sort of two, we'll do it over here, into two sort of chunks. So we have time equals 0, to time equals 4, and time equals 4, to time equals 10, right? So let's start by looking at what happens between 0 and 4. So 0 and 4, we have this little triangle here. And if we were to find the area under the curve here, it's going to be positive. So we're going to do 1/2 base times height. So the base here is 4, the height is 4. So we're doing 1/2 times 4 times 4, which is going to give us 8. And the units here are going to be meters because the velocity is in meters per second and the time is in seconds. So our change from time equals 0 to time equals 4 is 8 meters. And I'm going to say forward is the direction I'm going to assign it. You might say left, right, in the positive direction, but in the positive way, whichever direction that indicates. Now, from time 4 to time 10, we are below the x-axis. And so when we find this area, what I notice is that I have this trapezoid. So you can do the area of a trapezoid if you're comfortable with that, or you can separate it into a triangle and rectangle. Right? If we separate it like this, then we get this triangle, which is, I'm going to put an 8 here to indicate where I split this. From time 4 to time 8 is 4 units on the base and negative 4 units down. So 1/2 base times height. This is again 8. This is going to be negative 8. And then this little chunk here is 8 to 10. So that's 2 by negative 4. So that's another 8. So that gives us a total of 16 in the other direction. Okay. So that means from time equals 4 to time equals 12, or to time equals 10, we get negative 16 meters. And I'm going to call this backwards, but you can call it, to the left or down or whatever the opposite is than you said from 0 to 4 in the negative direction. Any of that's fine. But we want to get that area to talk about how much that object moved and in which sort of general direction. So for part B, we want to know the acceleration during the first 8 seconds. So I'm going to highlight the line that represents the first 8 seconds. Okay. So if we want to talk about the acceleration, we are talking about the derivative of velocity. So how do we talk about the derivative? Well, we see that the line is decreasing, so we expect the derivative to be negative. For us here, we see that this portion is linear. And so the derivative of a linear function is the slope of the line. So we can find the acceleration by finding the slope of this line. How do we find the slope of the line? We need 2 points on the line. So notice here that it's going to cross at 0, 4. That's where we cross through the vertical axis. And then I also see it crosses through at 4, 0, or I see that I have the point 8, negative 4, right? So any of those points will work. You could also find other points on this line. Any 2 points will work to help us get the slope of the line, which is the derivative, and the derivative of velocity is acceleration. So here, when I find the slope, I'm going to use these 2 points, 0, 4, and 4, 0. So the change in y, I have 4 minus 0 over 0 minus 4, which is going to be -1. I need to think about back how I find units. So I take the units of the dependent variable, meters per second, and divide by the units of the independent variable, seconds. So meters per second divided by seconds gives me meters per second squared. So the acceleration of this object is -1 meters per second squared during the first 8 seconds. So that means that the car is decelerating because it's negative. That means it's slowing down. The rate of change is slowing down over time. So part C says, during which time is the car accelerating, decelerating, and constant? So again, this has to do with when our function's increasing, decreasing, and constant speed. So for part C, we'll start with accelerating. We're going to be accelerating whenever acceleration is positive, which will be where velocity is increasing. So if I look through where that's happening, let's see. I can see that from 12 to 16, my graph is going upward. So time equals 12 to time equals 16. But then also from 20 to 24. So time equals 20 to time equals 24. So again, we're asking you to think back about the derivative and how we look at that on a graph in this particular context. So we're going to be decelerating whenever our graph is decreasing. So we see that that's happening from time equals 0 to time equals 8. So we're going downward. And then I don't see any other places where things are going downward. And then where is it constant? It's going to be constant wherever, we have these flat lines. So from 8 to 12. And then again from 16 to 20. And then lastly, 24 to 30. Oops, t equals 30. Okay, so we have 3 sort of things we have to consider, and we look at the behavior of the graph to help us answer these questions. Yeah, again, sort of linking back to what we learned in chapters 3 and 4. So that's sort of what we're trying to remember here. So for part D, suppose that at time t equals 0, the object is at its home base. Okay, how far away from the home is the object at time equals 4 and time equals 12? So this is where I think a picture is really helpful. So let's call home base, let's make it look like a house, right? And we have something moving, maybe it's a ball, maybe it's some other thing. But the first thing we want to find out is time equals 4. So we see on the graph that's something we already calculated. So at time equals 4, our object is 8 meters. We'll just make our object a ball here. Well, maybe 8 meters from home base. And that's t equals 4. So our little object, whatever it is 8 meters from home base. Right, at time equals 4. But then at time equals 4, we start going back towards home base, right? So, we kind of turn around and we're going to start going this way. So again, we have a triangle and we have a rectangle, and that gets us to time 10, but we also have to get to time 12. So here our triangle is from 4 to 8, and that represents 8 meters. So time equals 4, and then at time equals 8, right? Now we're back here where we started, right? So this is position 0 meters, because we were 8 meters away from home, and then we went -8 meters back, and we're at time 8. Then from time 8 to time 10, we'll put time 10 here. We've gone another 8 meters in this direction. So we'll label that another 8 meters. Now that's 8 meters from our home base. So now we're at -8 meters from our home in the other direction, but we still have to add on what's happening from 10 to 12. That's not one we've calculated yet. So from time 10 to time 12, right? We have a base of 2, a height of -4. So that's another 8 meters in this direction, which means we are now 16 meters from home base, right? But in the other direction. So at time equals 4, we are 8 meters in the positive direction. And then at time 12, we are -16 meters in the other direction because 8 of those meters was going back towards home. So again, I think for me, at least, I find these diagrams particularly useful, but the other thing we can do to figure out where we are at these times is add up the areas until that point, right? So if we're adding up 8 plus -8 plus -8 plus -8, you're going to get -16, right? Which is our conclusion. And so the negative just tells us we are going in the other direction than we started, okay? So there's a lot going on in this problem where we're thinking about things in a lot of different ways. It's good to sort of rehash these connections and think about them, but it definitely is a challenging problem overall. Okay, so our next application with area under the curve, fundamental theorem, all of this has to do with marginal cost and fixed costs. So when we think about back to business, right, we have cost, we have revenue, we have profit. The fundamental theorem comes up a lot with cost, and then oftentimes revenue and profit get brought in later. So let's talk about this. So when we talk about marginal cost, we're integrating C prime of Q. So the derivative of cost is called the marginal cost. And if we apply the fundamental theorem here, we have the cost to produce B items minus the cost to produce A items. This is the most generic form of applying the fundamental theorem. However, typically, our A is equal to 0. Why is that? Because we're talking about the total cost to produce X number of items. That means going from 0 up until that particular number. And as a reminder, C of 0, which is C of A in the generic form, right, represents what's called our fixed costs. So that's the total cost when you've produced 0 items. So we talked about how that might be like buying a machine up front or a warehouse, right? You haven't actually made anything yet, but you sunk some money into the cost. So that means that when we're thinking about total cost, we can say the total cost to produce B items, right? We would add the fixed costs over. So we'd have the fixed cost plus the change in cost over however many quantity we're thinking about. Okay, so if we want the cost to produce 20 items, it's the fixed cost plus the change in cost from 0 to 20, right? Similar to what we were looking at before, but now thinking about it in terms of business and cost. So let's look at an example, sticking with the graph theme for now. So the derivative of cost is the marginal cost. Suppose the marginal cost is given in the graph below. For part A, I want you to set up an integral to represent the total cost to produce 150 items of this product. So we're just setting up an integral. For part B, use the graph to estimate the total cost to produce 150 items of this product. So here you're estimating the area under the curve to help us answer what that integral represents. For part C, suppose there's an additional fixed cost of $1,000 to produce this item. What's the new cost now from part B to part C? For part D, suppose that you can sell this item for $25, write an equation to represent the revenue function and find the total revenue for selling 150 items. And then part E, find the total profit earned by making and selling 150 of this item. So as a reminder, profit is revenue minus cost. So you'll have the cost from part C, you'll have the revenue from part D, and then you can put those together to find profit. So I want you to take about 3 minutes, see if you can get all these things set up. Hopefully you can remember things like the revenue equation, but if not, feel free to go back in your notes to look it up, and then we will go through it together. All right, take about 30 more seconds. Okay. So for part A, we want to set up an integral to represent the total cost. So if we look up here at what our total cost integral will look like, we are trying to approximate the total cost for 150 items. So that is our B. So that's going to be fixed cost plus the integral from 0 to 150 C prime of Q dq. So this is what our generic integral looks like when we talk about finding the total cost. Okay. Now for part B, it says use the graph to estimate the total cost to produce 150 items of this product. So there's an underlying assumption in ignoring them, and we're saying, okay, what's the area under the curve for 150? Now, there's a couple different ways to do this. You could count blocks. There's a lot of different ways to approximate. So if you didn't approximate the same way that I did, that's okay. There's just a couple ways you can do it. So 150 is here. So we're trying to get the area under the curve between 0 and 150. So the way that I decided to do this is I decided to break this up into a rectangle that is here. And I noticed that I'm going to get a little extra area right here, but I'll show you why I think that's okay in a minute. And then also a triangle up here. And the true sort of part of this is that there's a little tiny bit of a gap right here on my triangle to the curve, which I think is about the same as this area here. So I think this will be a pretty good approximation of the area under the curve. So let's start with the rectangle. My rectangle here has a base of 150 and a height of 6. So this is counting by 2s. So when I multiply those together, I get 900. Okay. And again, this is all positive area because this is the x-axis, so everything is above the x-axis. And then for my triangle, I'm going to do 1/2 base times height. Now my base here is 100. If you look at where this little triangle lands, it's right above the 100. And then what about my height? So here, this is 12, 14, 16. For me, it's just about halfway between 14 and 16. So I'm calling this a height of 15. Okay, so I have 100 times 15 times half, and that's going to give me 400 and, oh wait, sorry, hold on one second. This is going from 6 to 15, right? So the height goes from 6 to 15. So that's a height of 9. Right? So 6 to 15 is 9 units. So I have half times 100 times 9, which gives me an area of 450. Okay. So if I add those two areas up, I get 1350 as my approximation. Now, like I said, there's a couple different ways you could do this. You could find the area of one block, which is going to be 50 times 2, which is 100, and then approximate the number of blocks. So ultimately, you should get something within the realm of like 1200 to 1500, right? No matter how you approximate it. So if you didn't get something in that realm, you may want to sort of think about how you might make that a little bit better. But I think this is a perfectly good way to do it. Or, you know, like I said, approximating one block to be 50 and then approximating the number of blocks you see under the curve. Okay, those are the two methods I think would work the best here. So for part C, it says, suppose now that there's an additional fixed cost of $1,000 to produce this item. What is your new cost to produce 150 items? So if we're adding on a fixed cost now, the change in cost was $1,350. The fixed cost is $1,000. So our new cost will be to add $1,000 to this amount, or whatever amount you approximated. So we get $2,350. $150 for part C. Okay, part D says, suppose that you can sell this item, I'm going to jump to D, for $25. We want to set up our revenue equation and then find the revenue for selling 150 items. So remember that revenue is price times quantity, and price is the price you're selling the item for. So our general revenue function would be 25 times Q, and we want to use that to find the revenue from selling 150 items. So we have 25 times 150, and that's going to give us $3,750. So the revenue that we bring in from selling this item for $25 is $3,750. For part E, it says find the total profit earned by making and selling 150 of these items. And as I mentioned, if we want the profit at 150, we need to do revenue at 150 minus cost at 150. So we said the revenue was $3,750. The cost is $2,350, which means that the profit, when we subtract those, is $1,400. Okay. Obviously, if your approximation is slightly different than mine, it'll impact this calculation, but you sort of get the process, right? So that's how we answer those types of questions and how we sort of bring in all the things we've been learning about economics and the fundamental theorem to work through these things. The next example here with economics is going to bring in something else we learned back in chapter 2.4, which is interesting. So let's see how this works. So the total cost in dollars to produce Q units of a product is C of Q. Fixed costs are $20,000. The marginal cost is given by this function here, 0.005 Q squared minus Q plus 56. We want to estimate the total cost to produce 150 units. So this is what we were just talking about. We have to make sure we bring in the fixed cost as well as approximate the area under the curve. Then we want to find the value of C prime of 150. So that's a plug and chug. We're going to be plugging 150 into the marginal cost function and interpret your answer in terms of cost of production. So what does that number mean? And then for part C, we're going to use parts A and B to approximate the cost at 151. So part C is asking you to do local linear approximation. So it's been a while since we've done that. It's coming on back for us. So again, you have to do parts A and B before we can attempt to do part C. And part A is based on the chapter 5 work we've been doing. Part B, we're just plugging into the function. And then part C brings us back to chapter 2. So I'm going to give you 2 minutes to see if you can work out these parts. Hopefully you at least get part A, which is what we're currently working on. And then we'll go through it together in 2 minutes to go through the other parts as well. It'll take about 30 more seconds. All right. So for part A, we're asked to estimate the cost to produce 150 items. So we know from the fundamental theorem that that should be the fixed cost plus the total change in cost to go from 0 to 150 of our marginal cost. And here we actually have the equation. So we can fill that in. And again, this will be dq to match the variable. And so we have to figure out what these values are. So for the definite integral, we can plug this into our calculator and we get 2,775. And again, that's in dollars, right? Because marginal cost is dollars per item. And then the independent variables items. So when you integrate, you get dollars. So the change in cost is going to be $2,775. But we also have the fixed cost, which is $20,000. So we've sunk $20,000 into this before we even made anything. And then when we made 150 of the products, that's how much additional cost we had. So we add those two numbers together and we get that our total cost is $22,775. Okay, so that's the cost to produce 150 items. For part B, it asks you to find C prime of 150 and to evaluate what that means. So we are literally plugging this into our marginal cost equation. We have 150 squared minus 150 plus 56, right? If we crunch that number, we are going to get 20.01. And remember that marginal cost is going to be dollars per item. So what that means is that when you are producing 150 items, it will cost you an additional $20.01 for each additional item that you make. Okay, that's the sort of interpretation we have here, because again, the derivative tells us how much we change to go one more item. So to go from 150 to 151, we expect the cost to go up by $20.01. So then for part C, it says use parts A and B to approximate C of 151. So if we have information about the function and its derivative, we can use that to approximate other points using local linear approximation. Local linear approximation says we're going to do the value we know plus the derivative at that value times how far away we're looking, which here we're going from 150 to 151. So we know that we were at $22,775 plus the derivative, which is 20.01 for each additional unit we make. And here we're going from 150 to 151. So we take the number we want minus the number we have. So times 1 here. So we're adding that $20 here. And so we get an approximation of our cost to be $22,795.01. Okay, so again, we're pulling in local linear approximation. If we want to approximate $160, we'd be multiplying by 10, or 160 items, we'd be multiplying by 10, so on and so forth. So that does go back to chapter 2, but it is sort of something that we know how to do and can apply here. We won't have time for the very, very last example. So if you're interested, you can watch that one on Moodle. There's just one example 8, so you can click on over to example 8, watch the very last one. Otherwise, that is the last application of the course, and you have now finished Calculus 1 material. So congratulations. I hope that you have a great rest of your week as you end all your classes. And as I mentioned, I will send an email out once all of the final grades have been updated in Moodle. So have a great rest of your day.